A survey of CAx methods, a knowledge floater by Bergische Universität Wuppertal, Department of Engineering Informatics. In engineering informatics, CAx techniques are used as a term to describe all processes that include the use of computers as a central part. These are design and engineering as CAD, computer-aided design, including the finite elements analysis for stress analysis. CAM, computer-aided manufacturing, that's machining and manufacturing, as well as CAQ, computer-aided quality management, for example by employing virtual crash tests. All these applications are summarized by the term computer-aided engineering, short CAE. A cardan joints fork will be used to give an overview over the different techniques. These parts' purpose becomes clear once you know that's parts of a vehicle's drivetrain. The solid model. At the center of all CAx methods is the solid model. It is created by an easy-to-learn, intuitive process based on sketches and the addition or deletion of basic geometric bodies. Upon completion of the solid model, several follow-up processes or process chains are available. This potential turns CAx techniques into the universal tool of modern engineering. Processes based on the solid model. Engineering drawings were digitally created based on the solid model of the joint fork. These are necessary for manufacturing, process planning, and documentation. It is very easy to develop variants of a part, for example in size, by using the given solid model. Assembly plans allow for the estimation of the right positioning of parts and their assembly options. In detail, producing a drawing, the solid model enables a semi-automatic creation of technical drawings. This process requires only minor drawing work and input by the user. The main advantage of such a drawing is its associativity. This means that it is still linked to the solid model and inherits every change of it, though the drawing represents the current state of the model at all times. Second, creating variants. All 3D CAD software offers the possibility to control certain parameter of the solid model. In example, here's the number of groups by an input box without the need to edit the solid model or the drawing. Parameterization enables much more than this. For example, it is possible to create tables for bore diameter and thread, and to automatically apply these values on the solid model. Third, creating assemblies. Certain software models support the creation of assembly based on several solid models. This combination of solid models can be used, for example, to simulate the real assembly process and check it for collisions. A special highlight. These assemblies can be used to create exploded views for assembly instructions. Another use is a movement simulation of parts of the assembly, for example in a gearbox. Further methods based on the solid model. A demanding use of the solid model is the simulation of stress. For this purpose, virtual forces that match the real loads are applied. This allows for the analysis of potential weak spots. To quickly manufacture examples of a part, rapid prototyping is used. These techniques require a solid model that is virtually cut in several layers to provide the necessary information for the rapid prototyping machine. Every slice of the solid model is then remodeled in plastics or metal, depending on the type of RP process used. Eventually, the tools required for drop forging or other manufacturing processes can be created based on the solid model and then used to produce said part. FEA simulation. The stress analysis makes use of FEA. The solid model is being divided in small triangular structures, so-called finite elements, similar to a wireframe model. The software detects weak spots by applying virtual forces at the model. The distribution and the amount of stress is marked by different colors. Though weak spots can be detected without the need for expensive and time-consuming tests on real parts. A noteworthy feature. FEA allows to calculate a part's behavior under different loads, for example tension, compression, bending or torsion. This requires only a few material properties, for example the elastic modulus, and an exact definition of the loads and boundary conditions. The computer is then able to calculate the effect of these loads on the part with a freely scale accuracy. This method is completely associative to the solid model as well. Rapid prototyping. Rapid prototyping is a common term for several methods that allow the creation of life-sized models or real parts within a very short time, even for complex parts. All these methods have an important detail in common. They all need a solid model dataset, which is later virtually cut into thin layers. This new dataset then is used as input for the rapid prototyping machine. This machine then creates a new part or prototype layer by layer according to the dataset. Finally, molds and dies for forging and casting. The molds and dies required for casting or forging processes can be manufactured easily by using CAD techniques. For this, there's a negative of the solid model created. All that is left to do then is to take into account process-specific requirements like drafts, runners and feeders to create a solid model of the mold or die.